Welcome to the deep dive. Today, we're embarking on a fascinating exploration into the world of software modeling and design.
hmm
Think of it like getting access to the master blueprints, the ones that guide how our digital world gets built.
Yeah, that's a good way to put it.
We've gathered a really rich set of sources to unpack, covering everything from the initial sketches, the visualizations, right up to the big architectural choices that define whole systems.
That's right. And the knowledge we've got today, it's pretty comprehensive. It covers foundational ideas like UML notation, lots of different software architectural approaches.
Like what specifically?
Well, you've got object-oriented, client-server, service-oriented, component-based, even designs for real-time systems and product lines.
Hmm.
Plus, we'll look at design patterns and, what makes software good, the quality attributes.
Wow. Okay, so it's quite the toolkit we have here.
It really is.
Absolutely. And our mission, really, for you tuning in, is to pull out the core understanding of how software gets thought up, designed, and then structured. We want to give you a clearer mental model, basically, of the fundamentals behind these complex digital systems we use constantly.
Yeah, peel back the curtain a bit.
Exactly. Okay, let's dive in. It's a huge area. Where should we start? Where's the foundation?
I think a logical starting point is just the fundamentals, the basic concepts that everything else builds on.
Okay.
So this covers the languages and notations we use to, describe the designs, the overall structure of a system, the architecture, and also the different ways we actually go about building software, the development life cycles.
Right. So first things first, how do we actually talk about software design? You mentioned notation. What does that mean in practice?
Yeah, software design notation. It's essentially the languages, the symbols we use to communicate a design.
Okay.
It can be graphical, like UML class diagrams, those visual maps of the system structure, or it can be textual, like pseudocode, which sort of outlines the logic in a more human-friendly way.
Now, UML is a big one.
UML is, yeah, the Unified Modeling Language. It's highlighted as a standard graphical language, especially for object-oriented stuff. And it's not just a common language. It can actually be a really powerful tool for finding inconsistencies in requirements early on.
Ah, okay. Catching problems sooner rather than later.
Exactly. But there's a catch. Its complexity can be a hurdle if you're not careful.
How so?
Oh, we sometimes see teams get kind of bogged down creating super detailed diagrams that don't actually help anyone understand things better.
Right, overcomplicating it. So it gives us the words, but we need to use them wisely.
Yeah.
Okay, what about the bigger picture then? The software architecture, what exactly is that?
Software architecture, yeah. That's
Mhm.
the high-level structure of the system.
The skeleton.
Pretty much. It's about identifying the main components, figuring out what each one does its responsibilities, and detailing how they all interact.
Okay.
And it's absolutely critical for things like modifiability and maintainability. How easy it is to change or fix the software down the line.
Like renovating a house with a bad foundation.
Exactly. You can't easily do it if the underlying structure is a mess.
It makes perfect sense. And the sources mention looking at architecture through different views.
Mm.
What are those key perspectives?
Right, the views. We usually look at three main interconnected ones. First, there's the static view. That shows the system structure, its parts at one point in time.
Like a snapshot.
Yeah, basically. Then there's the dynamic view, which shows how the system behaves over time. Often that means showing sequences of interactions between components.
How things happen.
hmm And finally, the deployment view. That shows how the software and its components are actually put onto the hardware and the infrastructure.
Where it lives in the real world.
Exactly. So these different views together give you a much more complete picture of the architecture.
Okay, so we have ways to describe the design, different views of the structure, but how do we actually build the software? That's where the software development life cycle, the SDLC, comes in, right?
Precisely, the SDLC. That covers the different methods, the models we use to guide the whole creation process.
Like the waterfall model.
Yeah, our sources mention the early waterfall model. Very linear, sequential, finish one phase, then start the next.
Kind of rigid.
It could be, yeah. Then came more iterative approaches, things like throwaway prototyping, build a quick, disposable version to figure out requirements,
Okay.
incremental development, build and deliver the system in small pieces, the spiral model, which adds risk assessment in each cycle, And then there's the Unified Software Development Process, or USDP.
And the USDP gets highlighted a bit. What's special about it?
Well, USDP is described as iterative and incremental. So the software grows through multiple cycles. It's organized into distinct phases like inception, elaboration, construction, transition. And it's driven by core workflows, requirements, analysis, design, implementation, testing, deployment.
Usual suspects.
Pretty much. And a key idea in USDP is the artifact. That's any tangible piece of information made or used during development, docs, models, code, you name it. And crucially, being iterative means you repeat these phases and workflows. You refine the software based on feedback and what you learn along the way.
So not one big bang release.
No, much more like a series of controlled, smaller releases that build up the final thing.
That makes a lot of sense. More adaptive. Okay, we've laid some really important groundwork here. Now, let's zoom in on modeling the structure. The source talks about static modeling. What are the key elements there?
Right. Static modeling, this is all about the stable structural parts of the system. And the basic building blocks here are classes and objects.
Classes and objects, okay.
A class is like the blueprint, the template. It defines the common features, the data, and behaviors, the methods for a type of thing.
Right.
An object is then a specific instance of that class, a real thing.
So car is the class.
And your actual car outside is an object of the car class.
Exactly.
Got it.
Blueprint versus the thing. And we draw these using class diagrams. What kinds of relationships do they show?
Yeah, class diagrams use boxes for classes and lines for the static relationships between them. The sources point out a few key types.
Like?
First, associations. These are just general connections. Often they specify multiplicity, like one-to-many, how many are linked, or if the link is optional.
Right.
Then you have whole-part relationships. These come in two flavors. Composition is a strong owns relationship. The part can't exist without the whole.
Like a car engine.
Right. If the car is gone, that specific engine, as part of that car, is gone too. The other is aggregation. A weaker has a relationship. The part can exist on its own.
Like a university and its students.
Perfect example. University closes, students still exist. Then there's generalization, specialization, that's inheritance. One class inherits stuff from a more general one.
Building on existing classes.
And dependency is mentioned too, often showing how groups of classes, like packages, rely on each other.
Okay, clear ways classes connect structurally. But what if the connection itself has important details?
Good question. That's where association classes come in.
Association classes.
Yeah. They let you model attributes that belong to the relationship itself, not to either of the connected classes. It's really handy in many-to-many relationships where some info is about the link, not the things being linked.
Like describing the link itself with its own class.
Exactly. Modeling the relationship as its own entity.
Interesting. And what about constraints? What do they do in these models?
Constraints are basically rules or conditions you apply to model elements.
Rules.
Yeah, to make sure they stick to business logic or limits. Like in a banking model, you might have a constraint on an account class saying the balance must always be 0 or more.
Okay, greater than or equal to 0.
Right. They help make the models accurately reflect real-world rules, prevent inconsistencies.
Ensures the digital model follows reality's rules. Now, the source differentiates static modeling of the problem domain and system context class diagrams. What's the focus for each?
Good distinction. Static modeling of the problem domain is about understanding and mapping out the key things, the concepts, the relationships within the actual problem you're trying to solve.
So the core business stuff.
Yeah. Often involves identifying physical classes, tangible things, users, other systems and entity classes, which are usually data-heavy, persistent information.
Okay. And system context diagrams.
They're all about defining the boundary of your software system, what's inside, what's outside.
The edge of your system.
Exactly. They help visualize the interaction with the external environment, hardware, users, other systems it talks to. And we often use stereotypes here, labels like input device, external system, user, timer, to classify those outside things.
So problem domain is the core concepts. System context draws the line around your software.
That's a great way to put it.
Yeah. Okay, really helpful. Let's switch gears now to how we model the behavior. Dynamic modeling. What tools and ideas do we need here?
Dynamic modeling, right. This focuses on how the software behaves over time, how the parts interact to get things done.
Okay.
The main tools here are interaction diagrams and state machine diagrams, which you might also hear called spate charts.
Interaction diagrams. Sounds like components talking to each other. What kinds are there?
Exactly. They show objects collaborating over time. We have communication diagrams. They emphasize the objects and their connections, using numbered messages to show the sequence.
Right.
Then there are sequence diagrams. They focus more on the timeline. Time flows top to bottom, showing when messages are sent and received.
More about the order.
Yes. And often, the message numbers on a sequence diagram match up with the communication diagram, so you can cross-reference them.
Okay. And the source mentions focusing on information passed between objects during analysis. Why is that important early on?
Well, during analysis, the main goal is understanding what information needs to be exchanged between objects to make a use case happen.
Just the what, not the how.
Exactly. Decisions about specific operations or whether communication is synchronous, like a phone call waiting for a response, or asynchronous, like sending an email. You don't wait. Those details usually wait until the design phase. Analysis is about the essential info flow. You don't want to get bogged down in implementation details too early.
Makes sense. Focus on what before how. Now, what about state machine diagrams or state charts? What do they show
Yeah,
us?
charts, yeah.
Uh-huh.
They model the different states an object can be in and the transitions between those states when specific events happen.
The object's life cycle.
Sort of, yeah. States are usually rounded boxes, transitions or arrows between them. You'll see an initial state, maybe final states.
Okay.
And the cool part is defining the events that trigger transitions. You can also add guard conditions rules that must be true for the transition to happen, even if the event occurs.
So event, then check condition.
Right. The notation is often like event condition, and you can associate actions with transition stuff that happens when the transition occurs, or entry actions happen when you enter a state, or exit actions happen when you leave.
So it maps out an object's life stages and exactly what causes it to change stage.
Precisely. A detailed map of its life and reactions.
And the source mentions hierarchical state charts. Sounds like adding layers.
It is, yeah, and it's really useful for managing complexity.
How so?
Hierarchical state charts let you group related states into bigger composite states. These composite states can then have their own nested substates inside.
Ah, okay, like folders for states.
Kind of. It helps organize complex state machines, makes them easier to grasp and maintain. Plus, you can do things like aggregation of transitions, where one transition defined on the outer composite state applies to all the substates inside it. Saves repetition.
Very practical for complicated objects.
Yeah.
So how do interaction diagrams and state charts work together in state-dependent dynamic interaction modeling?
Right, state-dependent modeling. It's exactly what it sounds like. Modeling interactions while paying close attention to the current state of the objects involved.
Combining the two views.
Yep. You use the state charts to know the possible states and transitions for an object. Then, the interaction diagrams show how that object talks to others, but, and this is key, those interactions might be different depending on the object's current state from its state chart.
Can you give an example?
Sure. Think of an order object in an online store. It might interact differently with a payment object depending if the order state is pending or processing or shipped. Certain actions are only valid in certain states.
Okay, so behavior changes based on state. That seems vital for complex systems. Lastly, for dynamic modeling, the source brings up active versus passive objects and message communication in concurrent systems. Key differences.
Okay. An active object basically has its own thread of control. It can kick off actions independently.
It runs itself.
Pretty much. A passive object, on the other hand, just sits there and waits for an active object to call its methods.
Okay, and concurrent systems.
Right. Systems where multiple things happen at once. Communication between active objects, usually via messages, can be asynchronous or synchronous.
We touched on that. Asynchronous is like email.
Exactly. Loosely coupled. Sender sends the message, doesn't wait, moves on.
Fire and forget.
Kinda, yeah. Synchronous is tighter. Sender sends, then waits for a reply before doing anything else, like that phone call analogy.
Wait for confirmation.
Right. And UML has specific ways to draw these different message types in diagrams. It signals that difference in coupling and waiting.
That's a great distinction. That leads us nicely into architectural design principles. The source talks about software architectural patterns. What are they and why are they important?
Architectural patterns, yeah. They're basically reusable, proven solutions to common problems you encounter when designing the high-level structure of a system.
Tried and tested blueprints.
Exactly. They give you a significant head start. The source distinguishes between structure patterns, how the system is organized into parts, and communication patterns, how those parts talk to each other.
Can you give an example of a structure pattern?
Sure, a really classic one is layers of abstraction.
The layers. Okay.
You organize the system into a hierarchy of distinct levels or layers. Each layer provides services to the one above it and uses services from the one directly below it.
Like the internet protocols, TCP/IP.
That's a perfect analogy. Application layer, transport, internet, etc. The great thing about layers is they help isolate changes. Change something in one layer, it ideally shouldn't break the others. Promotes modularity.
Makes it easier to change things.
Supposedly, yeah. The challenge, though, is actually enforcing those boundaries. If layers start bypassing each other, you lose the benefits fast.
Right. Discipline is key. So that's structure. What about communication patterns? How do the parts talk?
Well, the source highlights a few key ones. There's basic call return. One component calls another, waits for the result, then continues. Very common.
Like a function call.
Essentially, yes.
Yeah.
Then there's asynchronous message communication. Sender sends a message, doesn't wait. More decoupled, like sending that letter, you drop it off and go.
Yeah.
And then synchronous message communication with reply. Sender sends, then waits specifically for a response before moving on.
Okay.
Which one you choose depends on things like how tightly coupled components need to be, whether you need an immediate response, potential for blocking, lots of trade-offs.
Different conversation styles for components, each with pros and cons. Now, the source mentions specific architectural styles like client-server and service-oriented architecture, SOA. What defines them?
Okay, client-server. Pretty familiar. You have multiple clients asking for services or data from one or more servers.
Like a web browser and a web server.
Classic example. The server has the resources, the clients use them. Now, SOA, service-oriented architecture, kind of extends that. It's a distributed style where apps are built from a collection of autonomous, reusable services.
Independent services.
Yeah, that can be combined to create bigger business processes. Key ideas are loose coupling services don't depend heavily on each other's internals reusability, clear service descriptions, and often brokers or registries to help find and connect services.
Like a marketplace of digital services you can plug together.
That's a good way to think about it, yeah.
So SOA emphasizes independent, reusable services.
Hmm.
How does component-based architecture fit in?
Component-based architecture is very focused on building systems by assembling self-contained independent components with really well-defined interfaces.
Interfaces are key.
Absolutely. Components are meant to be reusable. They clearly state their provided interfaces, what they offer, and their required interfaces, what they need from their environment to work.
Like Lego bricks.
Exactly like Lego bricks. Each has specific connection points and does a specific job.
Great analogy. Okay,
Yep.
last one in the section. Real-time software architecture. What's unique about systems with strict time constraints?
Real-time systems, yeah. Here, correctness depends not just on the result, but also on when you get it. Timing is critical.
Deadlines matter.
Big time. Concurrency is usually a huge factor because they often handle multiple events simultaneously and have to respond within tight deadlines.
So lots happening at once.
Right. Key concepts include concurrent tasks, those active objects with their own control thread running in parallel, event-driven tasks triggered by specific happenings, periodic tasks running at regular intervals. And you need really precise specifications for task interfaces, TIS, and behavior, TBS, to manage all this and hit those time targets.
So it's not just right, but right on time, as a whole layer of pressure.
Yes, absolutely. Huge complexity increase.
Okay. Let's shift now to object-oriented design principles. We mentioned classes and objects. What core principles guide how we design them well?
Two really fundamental related principles are information hiding, often called encapsulation, and inheritance.
Encapsulation, hiding information.
Yeah. It means bundling the data attributes and the methods, operations that work on that data together inside an object, and crucially, controlling access to the object's internal details from the outside.
Keeping the insides private.
Right. It increases abstraction, reduces dependencies between parts of the system, makes things more robust, easier to maintain. Classes are the blueprints for these encapsulated objects, defining their data and what they expose through their public interface.
Okay. And inheritance.
Inheritance, or generalization specialization, lets you create new classes based on existing ones. They inherit common properties and behaviors.
Reusing code.
Exactly. Promotes reuse, helps model hierarchies, and abstract classes are important here too. They act like templates, defining a common interface for subclasses, but maybe not implementing everything. They leave specific behaviors for the concrete subclasses to define.
So hiding internals with encapsulation, building efficiently with inheritance, seems essential for good code. Wow, we've covered a lot of ground in this deep dive.
We really have.
What are the absolute key takeaways you'd want someone listening to really lock in about software modeling and design?
Okay, key takeaways. First, remember design happens at multiple levels, from detailed classes up to broad architecture. It's not just one thing.
Right, layers of detail.
Second, UML is that valuable common language for visualizing all these different aspects. Very useful.
Standard pictures.
Third, understanding different architectural patterns gives you those reusable blueprints for structuring complex systems. A huge help.
Don't reinvent the wheel.
Pretty much.
Yeah.
Fourth, OO principles like information hiding and inheritance are just fundamental for good, maintainable code.
Foundational stuff.
Fifth, dynamic modeling interaction diagrams, state charts, is crucial for understanding how components interact and behave over time, especially with concurrency and real-time needs.
How things actually work together.
And finally, maybe most importantly, the best choice of architecture and design patterns always depends on the specific needs, constraints, and goals of the project you're actually working on. There's no single right answer for everything.
Context is everything. That's a truly fantastic summary. Really clear insights there. We've certainly journeyed through a vast landscape of these digital blueprints today. So as we wrap up this deep dive, you hopefully now have a solid framework for understanding how software gets conceptualized and structured, from those basic blocks right up to the grand designs holding it all together.
Yeah, a mental map.
Hopefully it's given you a valuable shortcut, to grasping technical discussions more easily, appreciating the complexity behind the tech you use every day, and hopefully without feeling too overwhelmed by it all.
That's the goal.
Exactly.
And maybe one final thought, something for you to mull over.
Yeah.
Think about the software you use regularly, your web browser, maybe an app on your phone, online services. Can you start to see any of these patterns or principles we talked about?
Interesting exercise.
Is it client-server? Maybe some layered structure? Does it feel like components working together? Or maybe interconnected services like SOA?
Try to spot the architecture in the wild.
Exactly. And then maybe take it a step further. How might a different architectural choice have changed it? Would it be faster, slower, easier to update, harder?
How would different blueprints change the final building?
Precisely. Thinking about those kinds of questions will really help solidify these concepts, I think, and hopefully, spark a bit more curiosity about this whole fascinating world of software architecture.
A great way to end it. Thanks for taking this deep dive with us.